Hope your lunch wasn't too heavy, so you go to sleep. How are the Scandinavians doing with their jag? Almost over? So, all right. So we are ready to start on slide 102. And here is Tihomir.
We're going to now talk about how to do modeling with Bayes. And there's a lot of research in the Bayesian literature about labels. That's going to be one of our main concerns here, to how we deal with that. I'll just say some a general thing about what Mplus does. There's some really nice solutions in the literature out there about dealing with label switching. And Mplus actually has its own solution, so it's a little different from what you find in the literature. And the reason we do that is because almost these many solutions that are in the literature, they're not general enough. So for general purpose software, we actually have to come up with something simple, and that's what we did. So first, to explain what the problem is.
Say something.
Is it on yet or not?
No.
Oh, it's on. Okay. Okay.
Sorry.
So basically, what the issue here is with mixture modeling, and in why Bayes has a little bit of a hard time mixture modeling, is because technically, and the reason this happens is because generally speaking, classes are not identified per se. So, for example, here's a Mplus input, and you can appreciate here how simple this model is. So basically, a growth model, and we actually wanted to find an example to explain what Mplus does to prevent that. This is basically a manual, an example, the very first example, mixture example in the manual. So it's example 8.1 in the manual, and it has two classes. And for simplicity, we're going to work with just one chain to explain, again, the label switching. We're going to run 50,000 iterations on this. And basically, you have a growth model with 4 dependent variables at 4 time points, 0, 1, 2, and 3. And intercept and the slope of the growth model and regress on a covariate. And basically, if you run this particular output, like as I said, you can actually download the data. You know, this is a manual example, so you can run this yourself. And you run this for 50,000 iterations, and Mplus will not converge. And this is why. So back to the example here. The way the data is generated from this model, where in the first class, the intercept has a mean of 1, and in the second class, it has a mean of 3. So there's only one parameter in this mixture model that differs between the two classes, and this is essentially the only one parameter that I need to again, and let's also look at this. This is the histogram of that parameter. So what you see here is basically essentially the two symmetric bumps. Why it's not symmetric? Because it's not run infinitely long. If it's run infinitely long, then it will be completely symmetric. But basically here you have the class 1 with a mean of about 1. And then here's your class 2 with a mean of 3. And back to this trace, what happened is that the mean parameter, which is the main identifying parameter for this mixture, was running 2. And what happened is, the chain continued here and basically started exhausting the second bump in the posterior distribution, and it stayed here, and then it flipped back out here and continues like that. And if you run this infinitely long here means this is already 50,000 iterations. So I'm talking about like 5 million iterations. Then you're not going to see this, but 5 million iterations is not something you want to run in general. So plus there is something else. Now, even if you run 5 million iterations, it's completely meaningless value because it averages the value of this and this. So we are not interested into that. So we are interested in one. So again, you have k factorial symmetric bumps in the posterior distribution. We want to actually what we're interested in one of these bumps, and the way to difference is here now we gave starting values and labels for the main identifying parameter. And this parameter is called M1, this is M2, basically this is the mean of the random intercept. And then we introduce the following command, which is model constraint, basically which orders the parameters. So it's a simple thing as that actually will resolve the label switching option. Now, this parameter has to stay. This basically identifies the classes. Class 1 being the class with the bigger intercept mean, and this will be generated until the inequality is satisfied. So basically, you can sort of think of this as being that we're looking at the posterior distribution, but also conditional on these identifying conditions that actually makes the two classes not identical. They become unique this way. And if you run this model, and you look at the trace plot for that same parameter, now you don't see this problem anymore. You can see the parameter actually varies around 3, which is what it's supposed to do. And then the same thing in the histogram here, you only get one bump essentially. One thing to know about this stuff is that when you have more classes, then you basically need identifying conditions, unique identifying conditions to identify every one of the classes. So if you actually had 3 classes here, you have to introduce yet another inequality to identify the third class as being perhaps smaller than M2, with mean smaller than M2. And what you also want to know here is that that mixture does represent a little bit of a challenge in general. So, from maximum likelihood, if you've done mixtures, you already know that mixtures do possess multiple local maximum. That's just the nature of the modeling. Unless you have, infinitely large sample, then if you have very, very large sample, you won't have multiple local maxima. So you have this problem. One of the problems is this independent problem, right? That you can have multiple solutions in general with mixture models. Then you have the label switching problem. So in mixture models, actually, it's a lot more important to go to this trace line and make sure that only one solution is really being considered. Because even if you have a second solution, unique solution which is not label switching, then you actually might see that you probably see this in the trace plot. And you might actually need additional identifying conditions just to eliminate that additional solution. So here's yet another command that's useful here. In mixture models, you use the starts command. This is basically a maximum likelihood command to basically search for these local solutions and to find the best solution in terms of likelihood. And you can actually basically modify the code so that this same procedure that searches for local solutions is also used in base. So with this command, starts 120, basically what's going to happen is that 100 randomly perturbed starting values are going to be attempted using maximum likelihood. So this command is basically in combination with the starting value command. So st values equals ml means that the starting values for the Bayesian estimation is actually going to be the ML solution. And to actually come up with the best ML solution, then you use the starts equals 120. And again, this 100 basically represents 100 randomly perturbed starting values that will be attempted. They're attempted to about 10 iterations. Then the top 20 of them are finished. And at the end, the best solution that will be obtained from these two is going to be the starting value for the base estimation. And here you also have this command, which is the proc equals 4 starts. That actually command applies to the searching of the starting values, to the search for this local, the best ML solution. and it is independent of so with this command, you're actually going to get 4 screens, 4 Mplus running at the same time, dividing this number of starts into 4, and they're independently going to use the processor to search for the mixture. And here's another advanced model. It's a growth mixture model with multiple categorical indicators that in ML you cannot do this. Not just because of the you cannot do this with weighted least squares either. So that's truly the only estimator that can be used here, because you have a latent class variable on. So you have this again 9 categorical indicators measuring, a single factor, and that's repeated at 8 time points. So you get a total of 72 categorical indicators measuring these 8 factors, and then you have a growth model with intercept, slope, and quadratic term for these 8 factors. And on top of that, you have a latent class variable which actually splits the data into the several classes. So this particular model with Bayes, it's doable, and with maximum likelihood, it would use basically 8 dimensions of numerical integration plus the categorical variable, which becomes totally intractable. And again, the key thing is, with mixture is to monitor these trace lines, make sure that you don't have label switching of any kind. When you make the models, often if the model is not well identified, you're going to run into trouble with using Bayes analysis. So having a good identified model, simple identified model is always a good first step. And again, starting values to actually get you into the right framework, into looking at these classes is key. So anyway, I think this is Ben's coming on. Go.
Thank you. So do you, when you look for the switching of the labels in the trace line, do you recommend doing that with one single chain as the easiest way of seeing it?
Even with multiple chains, you can see it, I guess, fairly easily. And again, Mplus will not let it's going to determine that there's no convergence here. It will be fairly easy. So basically, the second chain is going to look somewhat differently. They will not go. It's not going to.
It's going like this.
Right. It could go like that, and then you'll be able to easily tell that the 2 chains are not identical at all.
Now, some of you frequentists, and I hear that there are a lot of you here today, may have run into an analogous problem when you do Monte Carlo simulations with mixtures. When you do like 500 replications, in one replication, class 1 may be the high growth mixture class, and the second replication may be class 2. So actually there was a structural equation modeling journal article by Twolevel and Lupke who had a routine for sorting out these things so that you put the right estimates for the right class and avoided that. It's the same kind of label switching problem that happens there, although in Monte Carlo studies. But in Bayes it happens in the estimation phase itself, and that's really puzzled Bayesians for a long time. And this is one solution, the restriction on parameters. Another one is this post-sorting of results that Stevens and others did.
Right.
But,
can I just say a little more? So
just a little bit more, though.
Yeah. In this example, for me to actually demonstrate the label switching, I had to play with the sample size. So what happens is, if you increase the sample size, then the 2 bumps will become sharper and sharper and sharper, and you won't be able to go from one chain to the other, because the reason you can go from one of the bumps to the other is because the tails connect of the posterior distributions. If you actually have a large sample, those tails will be so thin that they'll never connect. What happens if you decrease the sample size? If you make a sample size, say of 100 or 200, then what you end up is another interesting situation is where you have different local solutions that are not just the symmetric of each other. You actually get yet other solutions to work with. So it's an interesting thing to actually to work with this Bayes mixture. But it's doable, and we have good experience with that.
One tricky aspect, I guess, is if you have a mixture solution, you feel you have to do many random starts, and therefore would like to use ST values equals ML, but ML is not doable because of high numerical integration.
Right.
That's a tight spot to be in. So we're thinking about that one. Okay, so now, just to tell you where you are in this day, this morning we talked about path analysis and factor analysis. And now we're getting into more advanced topics. We talked about mixture modeling, and now we'll go multi-level. So we're following sort of the course of the 8 topics of the Mplus course sequence going forward here. So it gets progressively more complex as the day goes on. But that's just what you want, right? So we start with something relatively simple. The 2-level regression situation. So for instance, you have students within schools, and we're going to take a look at only a random intercept case here. So we have the usual notation. I think this is Rodenbusch and Breich style notation that they use in their 2002 book that I recommend if you don't have it already. So you have individual or student I in school J, say, intercept beta 0, which have subscript J, beta 1, the slope for X, and the residual. And in this case, you see that only the intercept is random, the slope is fixed. The intercept is random because we have this random residual U0 here. So we're going to take a look at that situation and see how Bayes estimation becomes useful, particularly when the number of, when J, cap J, is relatively small, a situation you often find yourself in practice. We're going to go down to J being equal to 10. 10 clusters, 10 level 2 units. We're going to have a simple case each with this an example with 50 students. And in this case, the intra-class correlation is around 0.1, which is a fairly typical level of intra-class. What did I do? Center predictor.
Oops. No, that's not going to work.
Just a quick reminder of 2-level regression in Mplus. You have variables declared as varying on the level 1, the within level, or you can have also variables on the between level, level 2. You designate a cluster variable, in this case it's clus, and you do typical 2-level analysis. We want to use Bayes. And you have a model that's declared on both level 1, level that is within. This corresponds to the model you have on the previous page in formulas, y regressed on x. And on the between, there's nothing there, really, except for the variance. So we're looking at, this is y on x. And on the between, we're going to estimate the variance of this and the mean of beta 0j, which is equal to gamma 0, 0. So that's all we need to say. And here now, we're going to be careful with choosing priors. In 2-level modeling, the issue is what priors should you use for the level 2 variance, for the between level variance? You know, what I label as B, which is the variance of U0 that we talked about in the formulas. And we're going to tell you a lot about this, but one very popular prior from the Bugs tradition, I call it the Spiegelhalter prior because it's mentioned often in the writings by this Mr. Spiegelhalter in the UK, who is part of the, or was part of the Bugs team turning into WinBugs. This is now an inverse gamma. IG stands for inverse gamma, and it's a prior. They call it IG eps. So epsilon is something that's small. So in this case, 0.001. And we're going to talk about that prior more in detail. But for now, let's just accept that that is a common prior for a variance parameter. And we're going to use it here in our Bayesian analysis. We're going to also take a look at the intra-class correlation, which is defined through the labels that we have on the model parameters as between variation divided by total variation, between plus within, as usual. So if we estimate this model, we have the within level parameter. That's y on x. That's the fixed slope y on x, beta 1. And we have a 95% credibility interval, which says that it's positive. We would think of it as significant in frequentist terms. And you have the within residual variance here. But we're going to be more interested in what's on the between level, on the cluster level, where we have only 10 cluster units. And we're going to be particularly interested in the variance of y. So this is, in the formula term, this is the variance of U0. Variance of U0 in the formulas that we had. So it's between level variance. So we want, for instance, to know how different are the schools. How much variation is it across the schools in this variance? And we see then that the 95% credibility interval, I'm trying to force you to think in terms of that, is not including 0. And so there is a sizable variance for the random intercept across the schools. And the ICC also bounded away from 0. Point estimates 0.223, 0.096. We're going to focus on that a little bit more. Here's what the posterior distribution looks like for the between level intercept variance. Certainly not normal, right? Certainly not normal. When it comes to variances, particularly in small samples, you have a very chi-square-like distribution for them. And median is 0.22 here. So that's the one we actually reported in the output. Intra-class correlation posterior also quite skewed, so that a symmetric 95% confidence interval that ML would give is not relevant. Now what if we did ML, two-level regression, with only 10 clusters, only 10 between-level units? Well, let's go straight, this is within, let's go straight to the between. This is a situation which we would like to do well in. Very often in practice we have fairly few clusters. What's the variance? Well, the point estimate is lower than for Bayes, 0.19. And this approximate Z ratio is not significant, but it's also probably very useless. You know, we don't know if we can use this. First of all, we don't want to test variance as being different from 0 by a Z-score, but it becomes even more problematic because we know that the posterior is skewed. Intra-class correlation, if you compare to Bayes, is also lower for ML and just barely significant by those kinds of the typical ML reasoning. So, conclusion, Bayes and ML disagree here. And we're going to dig into why they disagree and how they disagree by a few Monte Carlo simulation studies with small number of clusters. But first I want to suggest that you study a very good paper by Bill Brown and David Draper in the journal Bayesian Analysis from 2006. Two very good Bayesian statisticians, one in the UK and the other in California now, I believe it is. And they did a two-level simulation and real data examination of the importance of priors for level 2 variances. And they studied two priors. One was this inverse gamma epsilon epsilon with Spiegelhalter 1997 in the bugs literature that I referred to. And the other, Gelman-Rubin suggested, this is a uniform distribution. So, you know, think a rectangle, that's a uniform, which goes from 0 up to 1 divided by epsilon. statisticians love to talk that way, right? 1 divided by epsilon. That means epsilon is small. That means going from 0 up to something big. So it could be, say, this could be 1,000 when you divide by small epsilon. So they compare, those two priors played a prominent role in the paper. And they did a Monte Carlo study for a random intercept model with number of clusters varying from 6 to 12 to 24 to 48 with number of individuals within, total sample in parentheses. And with varying intra-class correlations, because that plays a role as well. So I recommend you read that paper. They found generally good results in terms of bias and coverage. They did sort of a frequentist Monte Carlo study. For the uniform prior, when using the mode as the point estimate. Not the median, not the mean, but the mode. And they also found good results for the prior B, the epsilon, inverse gamma, epsilon, epsilon, Spiegelhalter, using the median, which is the Mplus default. And they showed that we got poorer results in terms of bias and coverage for smaller number of clusters and smaller number of interclass correlations. That was their finding. Inspired by that, we did a Monte Carlo study in Mplus, and we stayed with 10 schools, each with 50 students. So that could be a fairly typical educational study, and a fairly typical intra-class correlation for achievement outcomes, for instance. And as a precursor to that, you can take a look at what the priors actually look like. Here's the Spiegelhalter prior. It goes up in a very high peak here at 0. It places a great weight on 0 as a likely outcome. It tends to drive estimates down towards 0 for the variances, which may be reasonable for level 2 variances. Here's an inverse gamma 1,1 density, and the way you read this, inverse gamma with parameters alpha and beta, the mean is beta divided by alpha minus 1. The mode is this, where A is called the shape parameter and B the scale parameter. In our second paper, the so-called Bayes advantages paper, Bayes using latent variable models, we actually have an appendix that describes how to think about these priors. And Timur and I were lately been talking about maybe providing a little prior calculator where you have simple input and the prior that you have to use is the output. That's particularly useful when you have priors for covariance matrices, which we'll get to soon. The so-called inverse Wishart priors. Now, in the Monte Carlo study, actually what I showed you before was one replication from a Monte Carlo study. When you do many replications, 500 or 1,000, I can't remember, here are the ML results for between. So you should, if you want to be pedagogical with your notes, you circle ML here, and then you circle between. So that's the across school variation, and then you circle variance and ICC. And you see that the ML estimate point estimate is a little bit low. That's the average. ML over the replication is a little low. And the ICC is a little bit low, which is exactly what we saw in our single data set analysis. More importantly, you may want to circle these two. 95% coverage, 81%, which should be 95, 81%. So the coverage is, in a frequentist way, is too low. So ML doesn't do well here. Now what if we want to do Bayes here? And let's first use a Spiegelhalter prior. And here's actually how the Monte Carlo study was done, in Bayesian two-level Monte Carlo. Same setup as in your usual ML, say, Monte Carlo study. And here you formulate the model in the population from which you draw the data, and you set the values up so you get the interclass correlation 0.1 in this case. And then you go ahead and analyze it. And in this case, we use the inverse gamma here. And you label the within variance and the between variance, so you can compute ICC, and you get the posterior for the ICC. That's what's nice. You get the posterior for anything that you define. And now we focus on the between level. So this is base, EPS, IG, EPS prior, base, between level, and variance. A slight overestimate, but not bad. And coverage, very good. And same for ICC, not a bad result. Coverage is close enough to 0.95. So that prior does well for this kind of situation. Now let's take Brown and Draper's other prior, the uniform 0, 1000. So we choose an epsilon small enough for the ratio to be 1 over epsilon to be 1000. And now, per Brown and Draper, we should use point estimate mode instead of median or mean, median being the Mplus default. We're on the between level. Variance 0.22. 0.23 is not bad. Coverage good. ICC, point estimate close to the true value 0.1. And coverage reasonably good. So that prior does pretty much equally well to the Spiegelhalter prior. Here's a prior inverse gamma minus 1, 0. And I mentioned that because in other contexts in Mplus it is actually our default prior for variance. But in this case, second level, level 2 variances, it may not be the best one. You see the point estimate shows to overestimation, although the coverage is reasonable. And the point estimate for the ICC overestimation, although the coverage is good. But that may not be the prior you want to choose for 2-level variances for this kind of setting. So if you have a real data situation, you can simulate and study these priors. You can choose the number of clusters that you have. Maybe you have 15, maybe you have 7. And the number of cluster members that you have. And the likely ICC, interclass correlation, that you have. Conclusions from this simulation: ML does poorly, base, good coverage in all cases, low bias except for that prior. So that particular situation can be handled well in base, which should open up a lot of doors. I often see studies where you have a small number of clusters and you worry about ML, and because the rule is that you should have what? At least 20 clusters, preferably 30 to 50 to maybe 100, at least for covariance structure models. And that may be impractical, unrealistic to have the funding to study that many schools. Here we can go down quite a lot lower. So found that exciting. Have you rested long enough now?
Yeah, actually, I want to go back to the mixture because I'm not done.
That's good.
Okay. So I want to say a few more things there. The first thing is we actually expect that base mixture is going to become a lot more important in the near future, because as we run more and more models, we'll be able to figure things out we cannot figure out with ML. So about multiple local solutions. Why do we have multiple local solutions in ML? We don't quite see it. We don't quite know where they are. Well, guess what? Base actually will show you where they are, because it goes through the entire posterior distribution and draws it for you. So you can actually see it in these histograms. When you have multiple local solutions, they'll show you up in the histogram. They'll be there. And it will be a lot of judgment to see how to deal with them, to whether to include them into your distribution of interest. But we see a big future actually for base and mixture, because it's so much more explicit. And we'll see a lot of development there. Another thing here is about this label switching problem. Is the question really is how do you actually know which parameters to use in this model constraint? I mean, I knew, because I generated the data, I knew that this is the only identifying parameter for the mixture models. But in a complicated model, you're not going to know. And then you have to find it. And you're going to find it into the trace plots. You're going to go in here, and you're going to look at this first parameter, and this is the mean, again, of the intercept in the growth model. And you're going to look at the same intercept in the second class. And you know what's going to happen there? It's going to be the total opposite. It's going to be here, and then it's going to go up here. And that's how you're going to recognize that these two parameters flipped. And not only they flipped the entire, mixtures. They basically flipped the entire classes. So that will actually indicate to you that you really need to use this parameter as the one that needs the model constraints to identify uniquely the two classes. And in general, this is still a very clear example. It's simulated data, and we separated the two fairly well. In general, it might not be very clear which parameter you need to use. So even if you, I guess practice will show how this works out.
Yep.
Yeah.
Good learning. 136.
Okay. So I'm back to 136, where we're going to now talk about another another problem that you can do with Bayes that you cannot do with ML. So this is a very simple example, really. It's a multi-level regression with a categorical dependent variable. If you ever tried to do this in Mplus or other programs, you know that if numerical integration is used, and you cannot have more than 3 or 4 dimensions. That's about as many you can have. So if you have 5 or 6 covariates or more, you're not going to be able to have random effects on these covariates. They're going to have to be fixed. So Bayes doesn't have this problem. Bayes can handle as many as you throw in. It's not computationally a challenge at all. So again, you have the number of random effects in such a regression. It's basically, you can think of this as being a Probit regression, a 2-level Probit regression, or a 2-level logit regression. And with each covariate, you essentially get a random effect as being the beta, the coefficient in front of the covariate. So again, with ML, you're not going to be able to handle more than 3 or 4 of these. You can use Monte Carlo integration in ML. However, the precision of that method is not as good. You're likely to end up with convergence problems, and generally the precision of the Monte Carlo integration is not very great. So the point estimates are actually going to be worse than if you use if you use Bayes. And again, the estimation time for ML will grow exponentially as a function of the random effects, the number of random effects, but with Bayes it grows linearly. So here's a simple simulation to illustrate some of the issues that you have to be aware of when you're doing something like that. And that's this example is from this paper that's on our website again. When you have multiple random effects and they're all correlated, you basically estimate the entire variance-covariance matrix of the random effects, the random slopes, and the random intercepts. They're all correlated. So the prior for that variance-covariance matrix that you estimate, it has to be this conjugate prior, that's inverse Wishart prior. So there's no option here, really. There's some technical options in Mplus. You can probably avoid that, but this is the standard thing to do. And it's basically, most papers when it comes to multivariate variance-covariance matrices, the prior is inverse Wishart. This prior is basically the reason they use it is because it's conjugate and it's computationally feasible. It mixes well. It mixes very well. The sequence will mix very well with this kind of prior. If you use some other prior, it's not going to mix as well, and the algorithms are not as efficient. So basically, one of the drawbacks of this prior is that actually it does not allow you. It's not very flexible in terms of entering prior information. So, for example, here's what it takes. It takes for the first term of the inverse Wishart is a variance-covariance matrix that you can aim for. And then this is basically a degrees of freedom. And this is divided to get the metrics that you are sort of sure that you think the prior is that you divide the first by the second. The meaning of this is also the degrees of freedom here. The way you think of the degrees of freedom is that what the inverse Wishart distribution does is basically it takes that many independent observations from this kind of a distribution, standard normal of this, and it basically computes the variance covariance matrix. So when you increase the degrees of freedom, that means you sample a lot more, and that means that basically the prior becomes stronger and stronger. So if you actually want to make a really informative prior, you might put some values like 300 or 400 here, and basically a particular matrix that you're after, if you know a particular informative prior that you want to achieve. But the point is that the reason it's not very flexible is because it kind of has the same, you have to make the same confidence level of informative prior for all the parameters. You cannot have different, say, more confident in the correlation than the variance. Everything is kind of goes together. And it basically is determined by these degrees of freedom. So far, it hasn't been that much of an issue because, generally, we haven't seen applications where that's much of a problem. So anyway, here's some popular values that we've basically been playing about. We've been playing with Mplus in terms of default priors. So these are basically priors we can put in, and you don't have to worry about it. That it works in almost all cases. So this IW0 minus Q minus 1. Q is basically the dimensionality of the variance covariance matrix you're talking about. And this kind of a prior basically is an improper prior. It has a density of 1 on the entire space of definition. So it's kind of a, say if you have an intercept and you want to put an informative prior from minus infinity to plus infinity, you put normal 0 infinity. And this is the equivalent for variance covariance matrices, that it's basically, it's completely uninformative. It has a constant density. All the values are equally likely. Now, we've basically been working on this, how to set up proper good priors for the Probit models and logit models. And there's a paper by Gelman that basically has sort of discovered this concept as weakly informative priors. And basically that weakly informative priors is this actually. So you can see, again, Q is the dimensionality of the variance covariance matrix. Because this is fairly small, the degrees of freedom, that means that it's not sharp at all. It's very vague, but it's not flat. So it actually has shape. Nevertheless, it actually brings this to some kind of a more set of reasonable values to work with. And it basically, our simulations show that that's the way to go. We don't even think about this much anymore. Whenever you have, you're working with logistic regression, the most of the parameters have weakly informative priors. They're not completely, they don't run from minus infinity to plus infinity, and that's very helpful in the estimation. Especially if you don't have informative priors, but you want good estimates, then that's the way to go. So this is basically the actually we use this prior for continuous models. In Mplus, that's our default prior for continuous models. This is a categorical model, so this is our default prior. The nice thing about this prior is that the marginal prior for the correlations is uniform on -1, 1. And that's a very nice thing to have. In general, if you're working with, you want to have an informative priors. The marginal for the variance is the inverse gamma with 1, 0.5, which has a mode of 0.25. We have, in these papers, we have these simple formulas that will tell you how this is computed. Also in Tech 1, which is the technical appendix in Mplus, this is actually computed for you. So the priors are reported, the prior means, the prior variances are reported in the output and the mode. Okay, and then here's another prior that we wanted to try in this simulation study. Basically, it uses twice the identity matrix, and this is the identity matrix I forgot to say that. And this is basically multiplies the identity matrix by 2. It gives a marginal prior for the variance of inverse gamma 1, 1 with a mode of 0.5. we use a fairly big sample size in this simulation, so 200 clusters of size 20. So we're talking about 400 sample size, 4,000. And you're going to see that here you can have potentially some effects of the prior, even though your sample size is large, right? It's 4,000, but in certain cases you will get some dependence on the prior. So we're going to basically be varying in the simulation study the number of random effects from 1 to 6. And here are the results. So basically this is the bias for random intercept variance, and that's kind of a representative parameter here. And you can see that the bias is generally, if you have one random effect, this is the coverage in the parentheses. The bias is very small. The coverage is excellent. The results don't change. They don't depend on the prior at all. When you have 2, pretty much the same picture repeats. When you have 3 random effects, the same thing repeats. When you have 4, you actually start seeing problems with the coverage. And this is basically with this totally an informative prior. Not for this prior, not for this prior. With 5 random effects, you start seeing some bias in here, although the coverage is still good. With this prior, it basically remains very good throughout. But with this prior, which is the totally uninformative prior, you actually can get some pretty bad results, which is bias of 0.19 and very low coverage. Again, that's our reason actually to choose this as the default prior, because it's a very simple prior that it doesn't rely on playing with. It's just an identity matrix, and basically we're after these properties that the correlation says uniform priors. We need to explain why this actually. How can you actually get to a better prior in this case? It's slightly better, right? There's not much difference here, but it's slightly better. Here is basically the kind of the motivation behind modifying your prior. It's kind of a iterative process of where you set the prior, you look at your prior and what you get as a posterior, and then you can decide if the prior is sufficiently good. So I'm going to illustrate this point a little bit later better. But what are the main conclusions here? First of all, that when you have fairly small, as you increase the number of random effects, the model becomes larger, and what we consider small, large sample is depending on that. The bigger the model, the more sample points you need. So you will to actually become independent of the prior. So if you have large number of random effects and your sample size is not as large, you can expect some dependence on the prior, and then carefully selecting that prior is important to actually get good coverage and good point estimates. And you can always do exactly the same what we did here. You can actually run your own simulation and see what needs to be done to the prior to obtain the best performance. So what is it about the third prior that actually achieved better results than the default prior? Basically, the variance of the mode is the prior is equal to the true value. Actually, this is flipped here. The mode of the prior variance is equal to the true value of 0.5. So for some reason, if you had an idea that the value should be around 0.5, and you will see this in the results, right? So let's go back here. Okay, so you're at this point right here, right? Or here, say. You have a value, the true value is 0.5. And you've obtained the value of 0.45 because he has a bias of this bias. in the original prior, in this prior, the mode is 0.25. So what you might want to do is actually adjust your prior to be corresponding to that mode of 0.45. And that's why you can multiply this identity matrix by 2, because if you multiply by 2, that essentially is going to bring your mode to 0.5. And once you actually get that, you get a little bit of fine-tuning of the estimates. So this is kind of what is sometimes referred to in the literature as ML-based priors. So you run a ML analysis, you get to certain estimates, and when you set up your priors, you choose a prior that's an informative or weakly informative that's fairly wide, but it has a mode around the value that you want, that the ML analysis gave you. Okay, so let's look at this other example, which actually is going to again go through this. What Bengt mentioned is actually, here we're going to illustrate another point with another advantage of the Bayes estimator, and that's basically that with ML analysis, when the variances are very small, if you've run multi-level analysis and the variance is very small, you've seen this, that basically it takes a long time for the program to converge. And there's some technical issues behind that, but basically it becomes, so let's look at this example. We generate data with random intercept, 2 random slopes, and one of the random slopes has a variance of 0. So, and again, 200 clusters of size 20. Bayes is fairly quick. It takes 5 seconds per replication. On the other hand, ML takes 19 minutes to converge. It basically, it's part of the ML algorithm. You have you're estimating also the mean of this random slope, and that particular mean is going to move very slowly because of the small variance of the random effect. So bottom line is ML has problems estimating models with small variances of the random effects. On the other hand, Bayes doesn't have this problem. It actually resolves it very nicely. And here, again, this is our default prior. I inverse Wishart with identity matrix and degrees of freedom 4. So in this simulation study, you can see here the ML estimates. Again, bias for all the parameters in the model, and 0 coverage is excellent, and Bayes being much faster pretty much gains again the same results. Maybe there's a little bit of a effect here. Again, this is the you have a little bit of a bias compared to ML, but again, this is those parameter estimates will be sort of dependent on the prior, and the most problematic one is here. So what I want to point out here when you run with Bayes is that okay, so first of all, you get a fairly large bias. This true value here is actually 0. That's what we had. We generated data with this parameter being 0, the variance of the random effect being 0. So basically we get an average estimate of 0.06 and coverage of 0. Now coverage of 0 is something you need to understand about Bayes, is that how do we obtain coverage with Bayes? We basically generate the posterior. We get 95% of the values. We make a confidence interval. And because all these values are actual values, they're true variances. They were true variances in some of the MCMC iterations. They are always positive. So you can never get anything but 0 here. And we'll talk about this in a second. But let's first tackle the problem of what can we do to actually get a little more precise estimate with Bayes and get this to be more precisely estimated to 0. Again, the conclusions here, though, Bayes avoids the slow convergence of ML. Bayes has generally small bias and acceptable coverage. And the only problem is with this parameter. So let's see. And this is what I was talking about how the prior and the posterior can contradict each other. So we have the inverse Fisher distribution. That's our prior for the variance-covariance matrix of the 3 random effects. The marginal distribution of the variance parameters is inverse gamma with value of 1 and 0.5, the second parameter. And this is basically the plot, f dot prior. So the mode is at 0.25. And basically what I'm trying to actually point out is right here, is this value right here, which is about 0.10 or maybe a little bit less, 0.8, where the prior says there are no values here. We actually gave 0 probability. We can actually draw another chart here that shows exactly the probability that what the prior gives is the probability that it's less than 0.1. 0.1 exactly, and it's 0. So we basically gave no chance to that parameter to converge to 0. We said the probability that the parameter is that small is 0. Okay, and what we get at the end is a value of 0.06. So you can see right away there's a contradiction, right? We disallowed all the small values because that's what our prior was. It just killed all these small values here. At the same time, our posterior distribution, this is the posterior distribution, but it's on a different scale, not here, that here's 0.06. Our posterior distribution, all the plausible values that we actually obtained, they were not allowed in the prior. So we can see that there's a general contradiction here between the prior and the posterior. And we eventually might actually implement something to make this easier to discover for when you do that. But in general, you should keep an eye on this. Are the priors and the posterior compatible? And you can see that this prior obviously was not appropriate because the results were basically out of the range. So what you can do here is you see this contradiction between the prior and the posterior. You see where the mode is. It's at 0.06. And you can basically choose the prior to have that mode. And the way to get to that is basically to change this is basically the model prior statement in Mplus language. Basically, this is the variance of the random intercept. This is the variance of the first random slope. This is the variance of the third random slope, and that's our problematic parameter. The default prior had a 1 here. And we're changing this now to 0.2. And this, actually 0.2, is going to move the mode of the prior from 0.25 down to 0.05, which will match what we got as a posterior in our first iteration, in our first analysis. And basically, these remain the same. Once you run this analysis, what you get is a random slope variance of 0.02, which starts to match what the ML analysis gave as a very small variance. And you can actually do this one more iteration on this, get the posterior and the prior, see if they match, and I'm pretty sure we didn't go one more iteration here, but if you go one more iteration, you're probably going to find out again that the prior and the posterior don't match, so you're going to have to decrease the prior even more. And at some point, this iteration process will stop at the point when you decide this variance is too small, I don't need this in the model. So basically, that kind of goes towards this important concept when you are working with random effects is how can we actually test for zero variance components? How do we test if there is really a random effect there, or is it a fixed effect? How do we know if the random effect has a non-zero variance and it's a real random effect, or is it just a fixed parameter that doesn't have a random variation across clusters? And that's a very important topic in general with multi-level models. And the literature is very technical. There's no clear-cut solution. What you need to know as a first few steps is the basic knowledge that you need to know is that, first of all, the maximum likelihood standard errors, they cannot be used to test for non-zero variance. And the reason that this cannot be used is because the value that you're testing for, which is the 0 value, is basically is a border value for the admissible parameter space. And the asymptotic theory doesn't really work when the parameter value is at the border. So this is basically is not really an acceptable solution to this problem, to the zero variance problem. Another possibility is to use maximum likelihood ratio test. But again, because it's a border value, the standard theory doesn't work, and this is not chi-square distributed. So, and the distribution is not very simple to figure out. It actually depends on the situation. There are some papers on that, but basically, it's pretty complicated. It's if you want to have a prepackaged solution, that's never going to happen here or here. That's my prediction. Okay, let's see what Bayes has to offer then for this problem. So, the first thing again to remember is that Bayes inherently we always have a significance variance because that's what the prior says. It is a positive variance. So if you give that kind of a prior, you can never expect this to go down to 0. I mean, it's not going to go down to 0. And if you have this prior, again, you cannot, testing against your prior is not, it doesn't make sense. So Bayes will always have a significant variance. If you look at the confidence interval of that variance parameter, it's always going to be, it will never include 0. So it will always be significant. So what we recommend is basically to do this iterative process where you get, if the variance is 0, you start with certain default prior, you'll find this contradiction where the estimated posterior is going to be way in the very close to 0, and the prior is not going to include these values. Basically, you can adjust this prior until the variance becomes so small that it becomes insignificant. And another way to sort of it's a little bit an unofficial way, I guess, to actually deal with this is you can use the inverse gamma of 0, 0. Now, this prior actually will include values that are allowed to be 0. And what's going to happen is if you actually use this kind of prior, you're going to get non-convergence. Basically, eventually, the program is going to run into, at some point in the iterations, the program is going to have, near 0 variance, and it's going to say that, it can't continue. But this is a more robust way because you always have control of what's happening rather than waiting for Mplus to reach non-convergence. All right. Let's see how we're doing with the time. I'm a little past, I think, but
that's all right. Well, that's the last slide before our break.
Okay. So, and here is oops, sorry. Yeah, here's another model basically that we wanted to show that can be done with Bayes. That's not doable with maximum likelihood. And look at the magnitude of how much this is not doable. So here you have, again, you have 8 time points, 9 categorical indicator per time points, and a growth model behind these 8 factors. And you have a 2-level version of this, basically. So each of the way this basically works is we always have for each variable, we construct a random intercept. So basically in the logistic regression, and those random intercepts are modeled with this second diagram here. And if you count the number of the dimensions of how many dimensions of integrations you're going to be using here, is either if you don't have residual variances on that second level, which is optional, you're going to have 2 times t dimensions of integrations for each of these factors. In this particular case, it's going to be 16. And if you actually include the residual variances, then it becomes t plus p, where p is the number of these variables, times t. And in this case, it's going to be 72 from this and 8 from this. So 80 dimensions of integration, which is it's just not imaginable that this will ever going to happen. So, and again, Bayes can be used to actually handle a model like that fairly robustly. So I think we are back to the question and answer session.
Just to tell you where you are now in this course, we have upped the technical difficulty level a little bit here. It's not just that you had a heavy lunch. So we started this morning with, and it's in the prior area that we've been working. So we started with fairly comprehensible, priors for things like slopes, that could be normal. And now we went to variance priors. We talked about the inverse gamma, and you can almost get a feel for what that is. But that was a single variance. But now we went to covariance matrices. And that's where it gets difficult to sort of understand what's going on until you've gotten into it and until we've simplified it for the user, which we can do in several ways. But inverse, covariance matrices have a Wishart distribution, and many of you may never have heard of a Wishart distribution, much less the inverse Wishart. And it's very hard to conceptualize the inverted covariance matrix, how that plays in. But there are some simple rules one can follow to be able to give intelligent priors also for covariance matrices, and some standard techniques then that one can use. So that's one of the most difficult areas. And now as we go forward, I will comfort you by saying that it's going to get easier. So you just passed the difficulty peak here. Now we're going to gently glide into the night. And that's from a book somewhere, into more application-oriented features, drawing on all this knowledge. So with that as an introduction, do you have anything to add?
I guess one thing to remember here is that, as you get into more complicated models, such as these Probit regressions with 6 random slopes, that's a fairly complicated model. I don't know if anybody has even published an application on this yet, right? So this is a very complicated model. What you should know that, you might have to worry about the prior. So it's always good to actually make this sensitivity analysis. And these are kind of some of the options you can do by changing the degrees of freedom of the inverse Wishart, and kind of put an effort into understanding exactly what these things are. And we work on our end to actually plot these priors that you decide to use, so that you know what exactly you have in there. But basically, again, even in these complicated examples, there was not that much dependence really.
Yeah.
The other thing I want you to guys remember is also that you have this the Gelfand's defined weakly informative priors, and they're in Mplus now, and they actually are key to getting this working so well right now. And so, don't be afraid of them. They're not the uniform, minus infinity to plus infinity. They have shape, they have mode, and it might not be the mode you want or the true parameter estimates, but they actually work. So
you said Gelfand, not Gelman.
Gelman. I think it's Gelman.
I mean, it could be either one, but I don't know.
Yeah, I hope so.
Okay, folks, we've talked enough. Now it's your turn. Who has a question after that? Yes, gentleman in the middle.
Can I get Mplus to give me an output file with the empirical Bayes estimates and the credibility intervals?
For what we call factor scores, perhaps? For random effects, you mean?
Yeah, for random effects.
We'll get to that when we come to plausible values, if you hang in here.
But yeah, the answer is yes. You can get the entire distribution.
That's one way to answer the question. That's way too direct. Yes, Dan.
At one point at the beginning when you were talking to Mary, you were talking about using processes equals 4 with the prevariance starts. And you said it pops up with 4 windows.
Yeah.
Is that available in non-Bayesian as well at this point?
Yeah, it's available for this purpose where you are...
Where you're doing a lot of random starts.
Right, you are searching. So basically what we have made available for mixture Bayes is to go through this random start searching engine that was developed for ML. So now you can do that before you do your Bayes analysis.
But
you just put the parens around the starts, and then it'll actually run them independently.
Right. It will run through independently, use multiple processes. So.
But when you see multiple windows on the screen, it never does anything Bayesian, right?
That's right. So yeah, when you see this, that's basically the ML section of the computation, and it searches through the possible starting values.
Okay, more questions, folks. You can do it. One more and you get coffee.
Maybe we need to ask them questions.
Maybe one soda instead. One more and you get Coke. Yes, there we go.
You mentioned that the label switching problem. I didn't look at the paper, but my impression was in a Monte Carlo simulation study, if you put it for extracting values, that would solve the problem. Does it or does not?
It doesn't always solve the problem if the mixture means, say, of a growth model lie too close to each other. You can still have the switching going on.
Yeah, if the sample size is very small, you can get the same label switching as in Bayes.
You have now earned your afternoon break. If you could be back here in 15 minutes, that would be great. 3:10, and we're on schedule.